Hello everyone. So today we will straight away go to the topic, that is adsorption from solution phase. So last session we have discussed the adsorption isotherm, isn't it? That is Freundlich adsorption isotherm. And there you have that formula, that is x by m is equal to k into p raised to 1 by n. Okay, and we have the graph. Okay. Now today we will see the adsorption from solution phase. That means what? The adsorbate is getting adsorbed on the adsorbent. And what is the adsorbate? The adsorbate is solute. Okay, you know in solution what all are there? Solute plus solvent will give you solution, isn't it? Now what happens in this adsorption? If we have a solid adsorbent, okay, for example a metal, or if you say a charcoal, okay, if you have a charcoal, then the solute from the solution will get adsorbed on this charcoal. Got it? For example, if I say you have an acetic acid solution, okay, acetic acid solution, okay, that means if you have an acetic acid solution here, acetic acid solution means what? Acetic acid with solvent is water, isn't it? So acetic acid solution is there, and if you put a charcoal into it, okay, if you put a charcoal into it, after some time what will happen? The concentration of this acetic acid decreases. Why that so? Why? Because you know this acetic acid is some of the acetic acid, that means the solute, will get adsorbed on this charcoal. Thereby, the concentration of acetic acid decreases. Correct? Okay. So that is all about the adsorption of the solution phase. Okay. The best example is acetic acid. Again, what about dyes? Dye means mixture of colors in a solvent, in a particular solvent. Now in that case also, if you add or put some good adsorbent like animal charcoal or activated charcoal, what happens? The color will get adsorbed on this solid substance. Thereby resulting you will get a colorless solution, isn't it? So that is how the solute is being adsorbed by the adsorbent. Okay, so you don't want to go into detail about it, but still the same way as the Freundlich isotherm, here also we have that formula, the empirical relationship as x by m is equal to k into, see, instead of, if you are taking gases, in the last session, in the adsorption isotherm, we have studied about the adsorption of gases on adsorbent, solid adsorbent. Here, since it is a solution, instead of gases, we will take the concentration. Okay, that is the only difference. That is C raised to 1 by n. Okay, so x by m is the, what is x? X is the extent of what? The solute from the solution, isn't it? And it is getting adsorbed on unit mass of that solid adsorbent. Is equal to K is a constant and C is the equilibrium concentration. Okay, the only difference is that equilibrium concentration. Okay, so K and 1 by n, you know, all other are same like what? Freundlich isotherm. So x by m, and putting logarithm also, what is it? Log x by m is equal to log K plus 1 by n log C. The same as we did in the Freundlich isotherm. Okay, so if you plot a graph also, you will get the same graph. What is it? Here it is log x by m. Okay, here it is log C. Then what is this intercept? Intercept is log k. And what is the slope? Slope is 1 by n. So, exactly the same as what you have seen in Freundlich isotherm. Okay, so it is easy to understand. If you know the Freundlich isotherm, this adsorption from solution phase is very easy. Okay. Then there are certain factors which affect the adsorption of a solute particle to a solid adsorbent. Okay, so what are the factors which affects the absorption of the solute particle from solution to what? To the solid absorbent. Isn't it? Sorry, adsorbent. If you have a solid adsorbent, say charcoal, you have a solution, for example acetic acid in water. Now, what are the factors which affect the solute, that means the acetic acid, into the solid adsorbent? Okay. Now, the first factor is, surface area. Surface area. What about surface area? If the surface area is increased, what is it? Absorption is also increased, isn't it? That is true for all physical absorption or chemical absorption. Wherever there is absorption, this is true for all absorption. That means if the surface area is increased, the absorption is increased. Okay. Now, the second factor which affects is the absorption decreases with increase of temperature. That is mainly desorption, isn't it? When the temperature is increased, what happens to the absorption or the absorption of the solute particles? It will get decreased. That is mainly desorption takes place here. Okay. So the second factor is, if the temperature is increased, absorption is decreased. Okay. Now the third factor is, what is the third factor? It depends on the concentration of solute. Definitely, isn't it? Because who is getting adsorbed? The solute particle is getting adsorbed. So definitely this absorption depends on what? The absorption depends on the concentration of the solute particles. Okay. And the last one is, it also depends on the nature of adsorbent and adsorbate. Okay, both adsorbent and adsorbate. Okay, so it both depends upon the adsorbent as well as the adsorbate. That means, simply speaking, it depends on the solid as well as the solute in this case. So these are the four factors which affects the absorption of a solute from a solution to the solid surface of an adsorbent. Okay, so it is very easy for us. So that's all, the absorption from solution phase. Clear? Okay. Now we will move on to the applications of adsorption. Okay. You already know, you get an idea of what are the applications, simple applications we are seeing in day-to-day life for adsorption. Okay, we have talked about a little bit. Huh? Now we will see in detail some of the applications for adsorption. Okay, now the first application here is the production of high vacuum. Now if for board exam the applications are asked for 2 marks, you get a very good point, 4 points in this application. Okay. Now first is high vacuum. That is the production of high vacuum. That means, if you make a vacuum through a vacuum pump, for example, but still it is not 100% vacuum. Okay, it may contain traces of moisture. So in that case, what you will do, if you put animal charcoal or activated charcoal, more than that, activated charcoal into it, what will happen? This activated charcoal absorbs the moisture and make it very, very pure vacuum. That is adsorption application, isn't it? That is adsorption of this moisture by means of this activated charcoal. So that is the first application for the adsorption. High vacuum, production of high vacuum, or even the traces of moisture can be removed from any substance. Okay. Now coming to the second is in gas masks, where this adsorption is connecting with this gas mask. See, in coal mines, the laborers who are working in coal mines, which is deep in the earth, the poisonous gases will be there. Okay. So in order to avoid this poisonous gas, they will wear gas masks, and in that gas mask, the activated charcoal will be there. Okay. So in this gas mask, they will put the activated charcoal so that only the good air will go into the lungs. Okay. So in order to avoid the toxic gases which is coming from the coal mines or any other thing, then there the adsorption technique is useful. That means that you know the activated charcoal can absorb the poisonous gases. Okay, the sulfur or like that. So that is the importance of gas masks in adsorption. Okay. Now the third is control of humidity. That you know, isn't it? As we have discussed earlier. That is, example is alumina gel or simple is silica gel. That we have discussed it earlier. Silica gel. Okay, where you will buy the new bags and all, there is a small packet of silica gel in it. We discussed it. Okay, they will absorb the moisture. Okay, now moving on to the fourth one, removal of coloring matter. That is also we discussed how the raw sugar, isn't it? The molasses, the raw sugar, how we convert into that whitish one, the whitish color. That is, the raw sugar is passed to the bed of animal charcoal, isn't it? Here, animal charcoal comes into play. Animal charcoal. So, animal charcoal will absorb the coloring matter. That is by dyes, isn't it? Like dyes, this animal charcoal will absorb the coloring matter and make it white. Okay, that we discussed earlier. Now coming to the separation of inert gas. How will you separate inert gas from the application of an adsorption or from the point of adsorption? See, you know the inert gases, right? Helium, neon, argon, krypton, xenon. Radon is radioactive. So, what happens in this case is, all these inert gases have different degree of adsorption. Okay, that means helium has got a different degree of adsorption than neon or argon, etc. So, depending upon the degree of adsorption, you can separate the inert gases by putting again activated charcoal into that vessel or container in which the inert gases are there. So, that is the separation of inert gases. Okay, that is also easy. And now coming to the sixth application is heterogeneous catalysis. Okay, already that part, after this session, the portion is catalysis. Okay, catalysis, that portion is deleted by this year. That is homogeneous catalysis and heterogeneous catalysis and also enzyme catalysis. So that three topics, small topics are reduced this year. But still, in heterogeneous catalysis, how the application of adsorption comes, see, I will just tell you what is that because you have to know that. See, homogeneous catalysis means that is, you know, a reactant gets converted into product, correct, in presence of a catalyst. Okay. Now, if the reactant, okay, say gas in the gaseous phase, if the product is also in the gaseous phase and the catalyst is also the same in the same phase, then this type is called as homogeneous catalysis. That means the reactant, the product and the catalyst are in the same phase. Then that type of reaction is called as, that type of catalysis is called as homogeneous catalysis. Okay. Now what is heterogeneous catalysis? Heterogeneous catalysis, now you have not noted. What is it? That is, if A giving B, for example, I will give an example, a true example, that is nitrogen plus hydrogen will give you ammonia. You all know that. Okay. To balance it. Okay. Now what happens is, nitrogen is in the gaseous phase. Hydrogen is also in the gaseous phase and ammonia is also in the gaseous phase. So, in order to have this reaction, you are using a catalyst called iron, solid iron. Now, what is the phase of this iron? Solid. See, the reactant and product are the same but the catalyst is in a different phase. So, in that type of catalysis, you call it as heterogeneous catalysis. Okay. Now, what is the connection between this application of adsorption and heterogeneous catalysis? That means iron acts as a solid and this iron, what happens in it? It will give the surface area for the reaction to happen. Okay, that we have discussed earlier also. That is, the iron acts as a catalyst. It provides the surface area for this reaction to happen. That is, here true chemical bond will be there. So, what type of adsorption is there? It is a chemisorption, right? It's a chemisorption. So, that is the application for the adsorption in heterogeneous catalysis. Hope you have got it, right? Okay. Now, coming to the very important application is the chromatography. Okay, in practicals you have to do that, the chromatography. The basic principle behind the chromatography is adsorption. Okay. There are so many types of chromatographies. For example, you are doing in the lab is the paper chromatography. Okay. Paper chromatography, you will do the separation of the colors in a dye. For example, if you put ink into the chromatographic paper, a special kind of filter paper, you call it as chromatographic paper, then you put it in a solvent, a suitable solvent, then the colors will come up according to the adsorption. Okay. So, if for example say in an dark or a black ink, if you put a black ink into the chromatographic paper, then after some time what will happen? The blue color and the red color will appear, okay, at different heights or different places. Okay, so the blue color, I think the blue color will appear first, that is, it is getting adsorbed first in that solvent. So the basic principle of chromatography is adsorption. There adsorbent and adsorbate are there, isn't it? Adsorbent means the paper, adsorbate means the liquid, the dye, isn't it? Okay. So then again there are another type of chromatography called thin layer chromatography, okay, TLC. Then column chromatography. So many chromatographies are there in which you have to find in practicals the RF value. Okay. So we will do that, yeah, in the lab. Okay. Now, so that is about chromatography. Okay. And what the last application is querying diseases. See how the medicine is connected with the adsorption. See, while taking medicine, the drugs will absorb the germs from the body and kill it. So in that connection you can say this application is also the querying diseases. Okay. There are also another application, so many applications. I think froth flotation process, where also adsorption takes place. Then in adsorption indicators. Okay. So just read out in the book and study 4 or 5 applications. Okay. So that is all about the applications of adsorption. So hope you are clear with this session. Okay. This point. Now we will move on to actually the next portion is deleted in your this year. Okay, that is catalysis, enzyme catalysis, etc. Now we move on to the next topic, that is, you know the topic, that is colloids. You know what is a colloid, isn't it? Now before going into that, in the smaller classes, we have studied 3 types of solutions. What are they? They are true solutions, isn't it? Colloidal solution and suspension. Are you remembering these 3? Okay. Now, depending on the characteristics, you differentiate the true solution, colloidal solution and the suspension. And what was the main criteria for this differentiation? That is the particle size. The particle size, isn't it? Now, true solution, the particle size we cannot see by the naked eye, isn't it? For example, a sugar solution or a salt solution, and it does not show the Tyndall effect, and it cannot be filtered through a filter paper, etc. Okay, but and the suspension, what are the characteristics? That is, the particles can be seen by the naked eye, isn't it? And it also shows Tyndall effect. Tyndall effect we will see in the colloids also. Just a recap what you have studied earlier. So in suspension, it can be filtered. For example, muddy water, mud and water, or clay or water. Clay is a colloid. Then chalk powder, the best example, chalk powder. Okay, you can filter it with an ordinary filter paper. And it also shows Tyndall effect. That means the light scattered. The beam of light can be seen through that suspension. Okay. Now, in the case of suspension, the other point is, if it is kept undisturbed for some time, what will happen? The particles will settle down. Okay. So, these are the characteristics of suspension. So, you all know that. Okay. Just a recap of it. Now, we are coming to the main thing, that is colloids. Okay. Now, what are colloids? Colloids are, you will say, heterogeneous mixture, isn't it? Heterogeneous mixture. Okay, what about the true solution? It is a homogeneous mixture. Now, what is the difference between a homogeneous and heterogeneous? Homogeneous means it is uniform throughout the solution. Heterogeneous means it is non-uniform. Okay, suspension is also a heterogeneous mixture. Okay, Now, why we say as colloid, or what is the particle size of this colloid? It's very, very important. The size ranges between 1 nanometer and 1000 nanometer. Very, very important. Okay. Depending on the size only, you are now going to make this. Okay. So, the colloidal size means it ranges between 1 nanometer and 1000 nanometer. Okay. Now, how a colloid is formed? How a colloid is formed? There are two parts in colloids, isn't it? What are they? One is dispersion medium and other is dispersed phase. Okay, these are all you studied in smaller classes. But still, what are they? That is dispersion medium and dispersed phase will give you a colloid. Okay, will give you a colloid, and the size ranges from 1 nanometer to 1000 nanometer. There is an analogy for this. That is, solution means what? That is solvent plus solute, isn't it? Just solvent means what? In a higher quantity. In the same way, dispersion medium is in a higher quantity. Dispersed phase means solute. Okay, that is in a smaller quantity or lesser quantity. You will get solution here, but here you will get the colloid. So, dispersed phase plus dispersion medium will give you a colloid. Okay. Now, dispersed phase can be what? Dispersion medium, a suitable medium. Example, water or any solvent, etc. What about dispersed phase? Dispersed phase can be something which can be what? Some macromolecules. What are macromolecules? Macromolecules are studied in solutions. That is polymers, isn't it? Polymers, then cellulose, starch, then proteins, etc. are macromolecules. So, this can be dispersed phase. When this, and again gelatin, rubber, starch, etc. can be dispersed phase. So, when this is mixed with the dispersion medium or any suitable solvent, you will get colloids. But what is the problem? It must be, the size must be, the colloidal size must be between 1 nanometer and 1000 nanometer. So, anything which comes under this range, you can call it as a colloid. Understood? Okay. So, this is about this colloids. Okay. So, then we will move on to the classification of colloids. This is just an introduction. What is dispersed phase? What is dispersion medium? Or what is the size of the colloids? That's all. Okay. Then it shows Tyndall effect. We will see the properties later in detail. Okay. Now, we will pass on to the classification means there are mainly three classification is there. One based on physical state. Okay. Physical state means what? Physical state of what? Dispersion medium and dispersed phase. What do you mean by that? That means if the dispersed medium is a solid and dispersed phase is a liquid, then what is that type of colloid? Or like that. Okay, that is physical state of dispersed medium and dispersed phase. Whether it is a gas, solid or a liquid. The second classification is based on the interaction of, okay, the interaction of dispersed phase and dispersion medium. That is the second classification, that is due to the interaction of dispersed phase and dispersion medium. Correct? And the third classification is depending on the size of dispersed phase. See? Dispersed phase I told you. That means comparing to solute, analogous to the solute, dispersed phase can be macromolecules, then starch, gum, gelatin, etc. Okay. So, then metals also, you will study it later. So, depending on these three classifications are made. Now, we will see one by one. We will see the first, how the classification is based on the physical state of dispersed medium and dispersed phase. Okay, we will see that in the classification. Okay. Okay. Now, we will see the first classification, that is about the physical state of dispersed phase and dispersion medium. Okay. Now, see this table. Are you remembering this table which you have studied? That is, depending on the physical state means whether it is a solid, liquid or a gas. Okay. Dispersion medium also solid, liquid or a gas. So, what is the type of colloid? So, one more question they can ask. what type of a colloid is when the dispersion medium is solid and dispersed phase is solid. Question comes like that. Okay. What is the type of colloid when the dispersion medium is gas and dispersed phase is solid? Okay. So that type of questions can come. So this table is very important. Or they can ask, give an example for an aerosol or give an example for an emulsion. Like that also they can ask. So study this table, and today itself you have to make this tabular column and write this in your notebook. Okay. So now coming back, if the dispersion phase is solid and the dispersion medium is solid, you can call this type of colloid as a solid sol. These colloids can be named as sol, S-O-L. Okay. The example is gems, colored gems, you know, these stones, that is that ruby stones, emerald stones, etc. They are the examples of solid sol. That means the dispersion medium is solid and the dispersed phase is also solid. The coloring matter you will get into the interstitial spaces, occlusion. So that is gems and glasses, thick glasses, example of solid sol. Okay. Now if the dispersion phase is solid and dispersion medium is liquid, then you can call it as sol, simple sol. If you want this mnemonic, SO, solid and liquid is L. So like that, sol, solid in liquid. You will say if dispersion phase is solid and dispersion medium is liquid, you will say the colloid is solid in liquid. In liquid means the dispersion medium. Solid in liquid. Solid means dispersed phase, the lesser quantity. Okay. So that is sol. Example is paint. You know paint. Then biological cell fluids are also the examples of what? Solid. So mainly it is very important, that is sol. That is solid in liquid. Example paint and cell fluids. Okay. Now third is dispersion phase is solid and dispersion medium is gas. Just imagine the dispersion medium is gas, atmosphere, imagine, and in the atmosphere the dispersed phase is solid. Then that type of colloid you call it as aerosol. And examples you see, smoke and dust. Smoke and dust means in the atmosphere the solid particles are there, isn't it? So that type of colloid is called as aerosol. And remember, whenever the dispersion medium is a gas, you call that type of colloid as aerosol. Okay, one more is there. See, dispersion medium is a gas, you term it as aerosol. Okay, so please remember that. Now, smoke and dust. Next is coming to liquid. Dispersed phase is liquid and dispersion medium is solid. So what it will be? It is called as gel. You know gel, no? Gel. So that is cheese, butter. Cheese means what? Cheese means it is a solid and the liquid is getting dispersed into it. Butter, cheese, etc. Gels, jellies, etc. Okay. Now next is liquid. Both are liquid. This is also important. That is emulsion. You name it as emulsion. Have you heard of emulsion? In soaps. Okay. Soaps and detergents. Emulsion. Now milk, hair cream, etc. are the examples of emulsions. Okay. Next is dispersed phase is liquid and dispersion medium is gas. So what is that? It is called as again an aerosol. Okay, so I told you, whenever the dispersion medium is gas, you call it as, the type of colloid you call it as aerosol. See, fog, mist, cloud, etc. Fog, mist means all what? The dispersed phase is, the dispersion medium is gas in the atmosphere, and if the dispersion phase is liquid, small water droplets in the atmosphere, we call it as fog, mist and cloud. Okay, depending on the dew point, when it forms. Okay, so that is fog, mist and clouds. And aerosol we talk about nowadays about the aerosol. So in the coronavirus, etc. So what it is that? It is that the gas in the atmosphere, this microvirus is there, isn't it? So it is called as an aerosol. Okay, that is why we call it as an aerosol. Okay. Next is the dispersed phase is gas and dispersion medium is solid. That is dispersion medium solid and dispersion phase is gas. The best, it is called as a solid form. And the example is what? Form rubber. Rubber means what? That in that rubber, form rubber, there is small holes in it where the air is xylene. Okay, or pumic stone. Okay, so that's all examples of gas in liquid. And sorry, gas in solid. And the last is gas in liquid. The dispersion medium is liquid and the dispersed phase is gas. Example is froth. That is foam. The type of colloid is foam and the example is froth and whipped cream. Or best example is what? Liquid. Gas in liquid. Soda water. That is the best example. You know that. Isn't it? The soft drinks. That is gas in liquid. Okay. So these are the 8 types of colloids. But when you come to gas and gas, why that type of colloid is not seen here? You know that gas and gas makes a homogeneous mixture. So it cannot be a colloid. That is why there are 8 types of colloids. So just go through it and have a look at it. Okay. So these are the 8 types of colloids, or the classification based on what? The classification based on the physical nature, the physical state of a dispersed phase as well as a dispersion medium. So you understood that? Okay. Now we will see the second classification, that is based on the interaction between the dispersed phase and the dispersion medium. So this dispersed phase and dispersion medium is going to interact, okay, to mix together. So then we see what is the classification. So second is interaction between the dispersed phase and the dispersion medium. So there are 2 types of colloids in this. By interacting this dispersed phase and dispersion medium, you will get 2 types of colloids. One is lyophilic colloids, okay, lyophilic colloids, and the other one is lyophobic colloids. Okay, lyophobic colloids. So 2 types of colloids you will get. One is lyophilic colloids and other is lyophobic colloids. You have studied hydrophilic and hydrophobic. Hydro means water. Philic means loving. That means water loving and water hating. In the same way, lyophilic means, lyo means the same thing, meaning that you can say it as solvent. Okay, lyo means solvent or liquid. Okay, now if the solvent is water, you can say what? Hydro. Hydrophilic and hydrophobic. Okay, so this is lyophilic and lyophobic colloids. Now we will see what are the characteristics of lyophilic and lyophobic. Okay, now before going into that, when we discussed about this emulsions and the different types of colloids, if you see the chemistry in everyday life, you see colloids are everywhere, isn't it? When you talk about paints or the biological cell fluids or the stones or the gold soul is there. Okay, now the precipitates which are there can be converted into souls. Okay, then the milks, then whipped cream, etc. The commercial product as well as the natural products, we can have colloids. Okay, and also one application for this colloid is that is firefight forms are, in the case of an emergency landing for an aircraft, if the aircraft has to land emergency, then what happens is the friction can happen and then it will get into flames. So in order to avoid that, you will put this colloidal solution or forms in the runway in order to prevent that friction. It is called as firefighting forms. You call it as that type of colloid. Okay, you will make this on the runway. You will fill this colloidal solution so that the friction will become less and it won't get into the flames, the aircraft. Okay, so that's again an application. Okay, so just to have an information, that's all. Okay. Now coming back to lyophilic and lyophobic, you can first say the characteristics. One is water loving or solvent loving, isn't it? You can say it is water loving or solvent loving. Now what about the lyophobic? It is water hating. Water, not water. We can say water means hydro. If it is hydrophilic, okay, this I can say liquid loving or solvent loving. Okay, here I can say liquid hating. Okay. Now second is, how will you prepare lyophilic salts or colloids? You can say both. Okay, lyophobic salts you can say, or lyophilic salts. The meaning is colloid. Okay. second is by the preparation of lyophilic colloids. How will you prepare lyophilic colloids? Okay. Lyophilic colloids, the preparation is very easy. You can just mix the dispersed phase and a dispersion medium. Okay. Dispersed phase in the sense you can have gum. Okay. You can have gum or starch. Okay. Or cellulose, etc. Okay. Plus a dispersion medium. Dispersion medium means a suitable medium, example water or any solvent. Okay. Now if you mix this dispersed phase and dispersion medium physically, you will get what? You will get a lyophilic salts. So the preparation is very easy. Okay. Now simple preparation for lyophilic salts. Now when you talk about lyophobic salts, it cannot be prepared easily. Just by simply mixing, you cannot have the lyophobic colloids. Now for lyophobic colloids, you should have special chemical methods. See, special chemical methods are there to form what? To form this lyophobic salts. Okay, that means in this lyophobic salts, if you add more electrolyte, you know, electrolyte, what is electrolyte? Electrolyte means, for example, say NaCl is an electrolyte. That means having ions. Okay. They will dissociate into the corresponding ions, that is electrolytes. Okay. Strong electrolyte means strong dissociation. Weak means only weak dissociated. Okay. So if you put electrolytes or adding more electrolytes, this will get precipitated. That's the main thing. Or in surface chemistry or colloids, you will say coagulation. What is it? Coagulation. Okay. So that is in lyophobic salts. Now the third is, you can say in lyophobic colloids, it is called as reversible salts. What is it? Reversible salts. Why you call it as reversible salts? Because you prepare dispersed phase and dispersion medium to get lyophilic salts. But if the lyophilic salt is evaporated, say, if you evaporate it, this gets back into the individual dispersed phase and dispersion medium. That means the process is reversible. Got it? The process is reversible. So that is why, then again if you want to make that lyophilic salt, you just add it. That's all. Okay. But here what happens? Once it gets precipitated, or once this lyophobic salt gets coagulated, it is very difficult to reverse back into the respective dispersed phase and the dispersion medium. Understood? So then you can call that to be irreversible salts. Got the point? Irreversible salts. Okay. Now you got the point. What is reversible and irreversible? Reversible means it can go back to the respective dispersed phase and dispersion medium. Here, once it happens, the precipitation happens, then it cannot revert back. That's it. Okay. Now the last point is, lyophilic colloids are always stable. Lyophilic colloids are always stable in nature. But this lyophobic are unstable in nature. Okay, so in order to make this lyophobic salts unstable, you need some agents, stabilizing agents you need. In order to stabilize, in order to have a stable form, you have to put some stabilizing agents like some electrolytes or something like that. Then it will be stable. But naturally, it is unstable and lyophilic colloids are stable. So these are the characteristics of lyophilic salts and lyophobic salts. That is the classification based on the interaction of dispersed phase and dispersion medium. Clear? Okay. So once again I will tell you, summing up. One is lyophilic, liquid loving, liquid hating. Then preparation by physical methods. Just simply put the dispersed phase and dispersion medium. You will get that colloid. Then here special chemical methods are needed. Once it gets precipitated or coagulated, it cannot be reverted back. That is why it is called as irreversible salt. Here, it can be reverted back by simple heating or evaporation. Then lyophilic is stable in nature, whereas lyophobic is unstable in nature. So I hope you are clear with this portion. Okay. Now we will move on to the third and the last method of classification, that is depending on the size of the dispersed phase. Now you are clear with what is dispersed phase and dispersion medium, isn't it? Now the third is depending on the size of the dispersed phase. See, size of the dispersed phase. Okay. Now coming to size of the dispersed phase, you can have three categories. One is, it is called as multi-molecular colloids. What is it? Multi-molecular colloids. The second one you call it as macromolecular colloids. Okay. And the third called is as associated colloids. So, associated colloids, or you can say this as Michels. Have you heard of this anywhere? Michels. In soap. We have studied soap earlier, no? So there it is Michel. So Michel is an example of soap, is a colloid. Okay. Now these are the three classifications based on the size of the dispersed phase. What is it? What are they? Multimolecular colloids, macromolecular colloids, and associated colloids, or you can call it as Michel. Right? Now we will see one by one. Okay. This is some simple topic, just theory, that's all. First is multimolecular colloids. Multimolecular colloids. Okay. Now from the name itself you know, multimolecular. What is it? Molecules. So many molecules aggregate together to form a large molecule. That is it. Multimolecular. Okay. Come together to form a large molecule. Okay, so that is multimolecular, which means small molecules. Listen, small molecules, mainly true solutions. True solutions have what? True solutions have size very less than 1 nanometer, isn't it? 1 nanometer. So that type of molecules, you call it as crystalloids. What is it? Crystalloids. Okay, true solutions. So you take small molecules of crystalloids where the size is very less than 1 nanometer. Then what you have to do? You have to aggregate it. Okay. Then you will have a colloid, and remember that must be in the size must be in the range between 1 nanometer and 1000 nanometer. See, this is a sol which is made up of the small molecules. Okay, the small molecules come together and form a colloid, but the range must be within this. Then you can say this is a colloid. This is a multimolecular colloid. So tiny molecules combine together to form a colloid. Okay, or a sol of having the correct range of size. That is what I told you. The particle size is very important. If the particle size is more than 100 nanometer, it will go to suspension. Correct. And if it is less than 1 nanometer, it goes to true solution. That is why we say always the size is very important. Okay, the range of the size limit is very important. Okay, so that is about the multimolecular colloids. For example, if I say you have sulfur molecule, SI molecule. Okay, this can be made into a colloidal sulfur by combining together, for example, more than 1000 sulfur molecules. See? Or you can have what? Gold sol. The gold molecule, 1000 gold molecules, small gold molecules combine together to form a gold sol. Okay, so these are the examples of what? Multimolecular colloids. It's very easy. Just the name represents it. Okay, so tiny crystalloids combine together to form a colloidal range. Okay, colloidal particle in the range of 1 nanometer to 1000 nanometer. Clear? Okay. Now, second classification is what? Macromolecules. Okay, macromolecules. First one is multimolecular colloids, and second is macromolecular colloids. Okay. Now, you know what are macromolecules? Macromolecules I told you. Example, proteins. Okay, peptides, proteins, then starch, then cellulose, then polythene, polymers, all the polymers, polythene, then acrylonitrile, etc. Okay, all the synthetic polymers as well as the starch, cellulose, proteins, etc. are macromolecules. Okay, now you see these natural polymers, I mean the natural proteins or carbohydrates or cellulose or starch will have the size of colloidal range. That means these macromolecules will have the size range between 1 nanometer and 1000 nanometer. So there is no need for combining together or for dispersing away. So naturally it is occurring in a colloidal form. That is it. That is called as macromolecular colloids. That means the macromolecule itself is having a size of colloidal range. So that is why it is called as a macromolecular colloids. Okay, for example, protein, okay, cellulose, then starch. All these are the examples of polymers. All these are the examples of macromolecular colloids. Okay, that itself you don't have to combine together or you don't have to disintegrate. Okay, making into small pieces. No, there is no need. It itself is in the colloidal range, that is 1 nanometer to 1000 nanometer. So that is macromolecules. Now one important thing in macromolecule is that, okay, that comes in the board exam question, that is macromolecules are stable in nature. See, macromolecules are stable in nature. Why? Why is macromolecule stable in nature? Why? Because, see, in these macromolecules, we already said that the size ranges from 1 nanometer to 1000 nanometer. That is why we call it as a colloid. Yes, but size ranges in 400 nanometer, which is towards the true solution side. Okay, that is away from suspension side and more towards the solution side. In that case, it acts somewhat as a true solution. That is why we say true solutions, you know, they are stable. Okay, but in the case of colloids, they are unstable in nature. But only in these macromolecules, we say they are stable. Why? Their size range mainly in 400 nanometer, which is more towards the true solution side. And you know true solutions are stable. So that is why we say that macromolecules are stable in nature. Okay, examples, you know, protein, cellulose, starch, etc. Okay, so this is the second classification of the size of the dispersed phase. Okay, now coming to the third type, which is called as associated colloids. Okay, in associated colloids, I already told you about machines. Okay, so in the next session, we will talk about how associated colloids are formed, now how the mechanism of the machine and the cleansing action of soap, etc. etc. Okay, so till now then, please go through the books thoroughly, read it. Okay, make notes. I'll ask you the notes within 1 week. So make note of it, give thorough reading. Till then, thank you.